So
Okay.
welcome everyone. In this week's first QTFMS seminar, we host Po-Shen Hsin from King's College London. He is going to talk about, as you can see, application of generalized symmetry in quantum computation. So you may start if you are ready, sir.
Okay. So thanks for the invitation, and sorry about the date confusion last week. So I'm going to talk about some application of generalized symmetries in quantum computation. So in this talk, the generalized symmetries are higher function symmetry and higher group symmetry. I'm going to explain what that means later. So the talk will be based on a series of works I've done with my wonderful collaborators. So there's a work about how to understand the logical operation or like quantum computation using symmetry, and how to build a very efficient quantum memory using generalized symmetries. And there are some upcoming works. And this is done with Ryohei Kobayashi, who is a postdoc at IAS, and Guan Zhu, IBM. There's also related works together with Mason Berkashli at Maryland, and Xie Chen at Caltech, Abi Dua at Virginia, Changming Jian at Cornell, and Chen Geshi at Santa Barbara. So before diving into detail, let me give you a brief history of quantum computing. So quantum computation is originally invented by physicists like Feynman, Manning. So they suggest that quantum computers can simulate quantum dynamics much faster than classical computers, so exponentially faster. And quantum computers are based on quantum mechanics, and they are prone to errors. So in order to make the quantum computers work, you need some error correcting scheme. And the first error correcting scheme is discovered by Peter Shor back in 1994. And there is a connection between quantum computation and gauge theory discovered by Kitav later in 1997. So he discovered that we can use gauge theory to build models for quantum computers and like spreadings of onions to and later on, Kitav and independently by Neil Laflamme Zurich, they discovered the threshold theorem, namely that even if quantum computers are like faulty, like each elements in the quantum computers can be faulty, they are errors, but as long as the error is sufficiently small, you still have a working quantum computer. So that's the threshold theorem. So if your quantum computer has a threshold, then it's a working. Now, and later on, importantly, Freeman, Larson, and Zheng Wang, they show that non-abelian onions, which exist in the dimension, use the braiding of non-abelian onion, they can realize universal quantum computing. And they can use the braiding to implement any possible computation steps. And more recently, I guess 3 years ago, Pentilif and Lachev, let's discover a asymptotic equal LDPC code. So what the importance is that it's a quantum codes that have more particle applications. So those are quantum codes that can store more information as you increase the size of your computer, and can correct the errors, correct more errors as you scale up the quantum computers. So it's important for particle purpose. And later, last year, Google has demonstrated that their processor can reach the critical error threshold. They successfully reduce the error such that as they scale up the size of their quantum chip, the error, the final error, the logical error, actually becomes smaller. So, the important breakthrough. And this year, Microsoft has some roadmap for topological computation. So that's a brief history of quantum. Now let me back up a little bit. So why is quantum computing important? Well, the importance is that we can use quantum computers to tackle a certain computation demanding task exponentially faster than classical computers. There's many applications such as quantum chemistry simulation, so you can discover new material, or you can use quantum computers to to have more secure financial encryption. And the basic idea is to replace the classical bits on your classical computers like 0, 1 by orthogonal quantum states, 0 by one state and 1 by another state. And the logical operations are unitary operators acting on those quantum states. So it can act on single multiple qubits. So on quantum computers, the quantum states are called qubits. And the basic idea is to encode your logical qubits, encode your logical information as the ground state wave function of some gap lattice model of many, many physical qubits. So encode your logical information using many, many physical qubits. Now, the presence of gap is important because gap can provide some robustness. So if you perturb the system a little bit, as long as it's below the energy gap, you still have the same ground state wave function. So that's the basic idea. Now, where does the symmetry come in? So if you have this gap many-body lattice model, you can have emergent symmetry. So the symmetry can preserve the ground state subspace. It leaves the ground state of your many-body gap lattice model invariant. And as I mentioned before, the ground state wave function encodes the logical information. So that means that those kind of symmetry will will act within the logical qubit. So we will map one ground state to another ground state. So they are logical operations on your quantum computers. So for example, if you have just two copies of your gap lattice model, and there is an exchange symmetry, not just exchange or swap all the physical qubits of these two copies. And of course, you will also exchange the ground state wave function. So this kind of exchange symmetry or swap symmetry is a logical operations on this quantum computer. Now, it's important that the logical operations have to be fault-tolerant. Namely, if you have some error somewhere, like in this picture, let me open the pointer. Can you see my pointer? Okay, so
Yeah.
Okay, so if you have some error here, you want the symmetry or logical operation to be such that after you apply the logical operation, the error does not spread too much. So this requires that the symmetry or this logical operation will have to be locally preserving. Namely, if there's a local operators sitting here, if you apply the symmetry, the support of the operator will not spread immediately infinitely far. So this is an important requirement for the symmetry. So this is going to be the case that we discussed. So for example, the symmetry can be on site, and then it's a product of operators that acts within each site, and this is called the transversal gate. Or more generally, the symmetry can be generated by finite depth local unitary, and then it's a unitary circuit, but a depth, like the width here, will be finite. So the spread of the error will be finite. So there are some desirable properties we would like to have for those symmetry or for those logical gates. So one desirable property is to be able to apply the logical gates in parallel. So if we can apply like different logical gates on different logical qubits at the same time, it will save the resources. So can do some parallel computing. So that's one important property. Another important property is to construct universal logical gates. So we want to realize all the possible computation steps on your quantum computers. And an important ingredient of these universal gates are the so-called non-Clifford gates. So Clifford gates are a subset of logical gates that can be efficiently implemented on classical computers. So if you really want to utilize quantum computers, you need to construct non-Clifford gates. So Clifford gates are unitary operators that map Pauli operators to Pauli operators. The non-Clifford gates will not do that. So and this is important for realizing all the possible computation steps. So this is an important requirement we like to have. However, so there are some non-universal gates in the literature. However, this non-universal gates may not be efficient in every quantum algorithm. So for example, there can be quantum algorithms where a particular gate appear many, many times. But this particular gate can be a very complicated combination of the universal gate set people already know. So in this way, this algorithm cannot be implemented efficiently because every time when you call this like common gate, you have to perform this complicated multiplication. So this is not very efficient. So it's more desirable to be able to engineer some common set of gates in many quantum algorithms. And one popular submodule in many quantum algorithms are quantum Fourier transform. And we are going to we are going to talk about what kind of like how to build some common gates in quantum Fourier transform, so we can efficiently implement it in many quantum. And so another thing about symmetry in quantum computation is the quantum memory. So you can think of quantum computers as consisting of the storage part, namely quantum memory that can store your quantum information, and also logical gates, namely how to operate your. Now there are two types of memory. So one is called non-self-correcting. So non-self-correcting memory will require repeating error correction on your content information. And because basically quantum computers are faulty, so you need to repeatedly perform error correction. And in order to correct the error, you need to measure where the errors are in your quantum memory, and then use a classical computer to figure out how to correct the errors. So this kind of non-self-correcting memory is more costly. It's not very efficient. And more desirable memory is self-correcting memory. So this self-correcting memory does not need a classical computer, and the error will just automatically disappear. So it's more desirable. But it's hard to find self-correcting memory in low dimension. So they essentially correspond to topological field theory or topological orders without any particle excitations. So once your systems have particle excitations, you'll have many, many errors. And there are only limited systems that have this self-correcting property that have been studied in the literature. And some of them have been realized in experiments using Java AI. So one advantage of generalized symmetries is that if you gauge the generalized symmetries, so for example, if you gauge a higher phone symmetry, so you have some higher phone gauge field, like two phone or three phone, etc., you can use those higher phone gauge theory to construct models with these self-correcting properties. So for example, we have been able to use those higher phone gauge theory to construct the first non-abelian self-correcting memories. So this is a new type of topological orders that can self-correct the errors, and it's also thermally stable. So as you increase the temperature a little bit, you still have the quantum. Okay, so let me
Sorry,
just
before
yeah.
before proceeding, can I ask something?
Yeah, sure.
In this, in your proposal, you say that 4+1 the loop Tor code and 6+1 the color code. As we
Yeah.
know, in the low dimension, we are usually, how can I say, used to deal with onions and their braidings when consider topological quantum computation. What are these extra dimensions? Are they synthetic or some maybe flavored dimensions?
Right, so let
Because
me first tell you what they are. The usual topological orders like onions, they have particles because onions are particles. So onions are not self-correcting. So that's all of the question. So those models like the loop torical and the conical, the minimal dimensional excitations are loops. So instead of particles, they have loop excitations. And they are in 4+1 dimension or 6+1 dimension. So how do we realize those higher dimensions, like extra dimensions in the lab? So the idea is that, well, let me give you an example. So if you have a cube, okay, so and you want to realize the cube in 2D. So one way to do that is by like squeezing the cube down to a plane. And then you will see that you can realize the cube on the plane, but there's some overlap, like there's some crossover. And this kind of crossover is essential to realize this kind of higher dimensional systems, like in particle, like physics dimension. Yeah, and that's basically what they are doing. So in the lab, they have trapped ions. So ions basically are movable, so you can just change the where you put the trap to move the ions. And because ions are movable, we can have some kind of long range connection, like this kind of crossover that I told you earlier. So in this way, they can realize like higher dimensional system using this kind of non-local connection. Yeah. So that's
So,
particularly, yeah. Mhm.
so in this aspect, this looks like an analog quantum simulator, right? Because we are using trapped ions
Mhm.
to to do experiments.
Mhm. Right. Yeah, I mean,
Okay,
the only novel thing is here is that they need some kind of non-local connection. Like you need some kind of like highway for anion to move for the ion to move from one place to another. Yeah. So we need some kind of long range connection. That's the essential part.
thank you.
Yeah. Are there any other questions? Okay, so maybe let me just briefly mention some other motivations. So as I mentioned earlier, common codes or or the logical qubits are ground state wave function of many-body graph systems. So if you discover new common codes, it means that you discover some new many-body graph system. So it corresponds to some new phases of matter. For example, like the fractal phases of matter, where the particles are like immobile or can only move in particular direction. This kind of novel phases of matter are originally motivated by quantum information perspective. And also studying the logical gates and their computation correspond to the symmetry of the system. And symmetry is important to understand the dynamics. So for example, you can ask, can we engineer some given quantum codes using some complicated lattice model? And one way for this to happen is to study where this complicated model has these symmetries correspond to logical gates. And also, as I also mentioned, quantum codes can realize like topological systems above physical dimensions using long-range connection. So this is well, to me, this is the only way to realize those like 4D system or 5D system in the lab. So this is one way to realize this higher dimensional system. And also, common codes can also help understand new mathematical structure, like higher fusion categories, which describe a higher dimensional topological system. So it's also important for mathematics. And there's also some other mathematical application, but I'm not going to talk about that. Okay. So here's the brief outline. So first, I'm going to introduce some basic quantum codes I'm going to discuss, and then tell you how like higher function symmetry or generalized symmetry can help discovering some logical gates in the system. And then I'm going to show how to use those higher symmetries to discover logical gates that can implement quantum Fourier transform more efficiently, which is important in many algorithms like Shor's algorithm or quantum machine learning. Okay, so let me skip the detail. So for my purpose, I'm going to focus on a simple ZN gauge theory or high function gauge theory with a discrete ZN gauge field. And most of the time, I'm going to take infinite 2. So Z2 high function gauge theory in some D space-time dimension. So we can describe this higher function gauge theory using a two gauge field. One is A, the other is the dual gauge field B. So you can think of B as the electric field, A is the gauge field, and you have this action. So B is a Lagrange multiplier that forces A to be to have Zn. And so this kind of Zn gauge theory, if you put it on a space, then the space will then you will have some degenerate ground states on the space. The degeneracy like so cohomology will count how many Zn connection in space. And this dimension also tells you how many logical qubits that is stored. So remember that logical qubits correspond to ground state wave function. So if you have two ground states, you have non-trivial number of logical qubits. And you
Po-Shen,
can, yeah, sure.
can I interrupt? Your voice
Yeah.
just came back and forth. We can't hear you very well.
Let me increase the volume. Is it better? Hello?
Yeah, it's better.
Okay.
Maybe it's about your internet, but I'm not sure for now. Yeah. But
Okay,
it's better now.
let me try to increase the volume a little bit. Okay, so this kind of ZN gauge theory will be central to my discussion, and this ZN gauge theory can be described by a lattice model. So it's a gap lattice model. So the lattice model has two terms. I'm going to use Z to label the gauge field. So if this poly Z is +1, then the gauge field on this place where you put the Z will be trivial. If the poly Z is -1, then you have a non-trivial gauge field. And similarly, this X will play the role of electric field. So for example, if D equal to 3, namely the space is 2-dimensional, and if you have a square lattice, then the Hamiltonian consists of this kind of two terms. So you have so for each vertex, like this black dot here, you put poly X on the four edges that are adjacent to the vertex. So this term basically equals to the Gauss law operator, the divergence of the electric field, because poly X is the electric field. Another type of term is the Parquet term, where you put the product of poly Z on the boundary of the face. So this is a small holonomy. This is the holonomy of small Wilson loop around this block. So this is usually called Bloch's term. And this is the only two terms, two types of terms in describe ZN gauge theory. So in ZN gauge theory, the gauge field is flat. So that tells you a small holonomy, like small holonomy will be trivial ground state. And also you need to obey the Gauss law constraint. This is okay. So what kind of symmetry is present in this model? So first of all, there are Wilson operators. So Wilson operators are product of poly Z operators on a closed loop on your lattice. So these Wilson line operators commute with the Hamiltonian. So it's a symmetry of the model. And you can also have a monadic operators, like the space is 2D, monadic line operators on a closed loop on the dual lattice, where you put the product of poly X on the edges that intersect with this closed loop. And they correspond to basic logical case. And later on, I'm going to talk about many other gates present. So let me skip this. So let me just briefly introduce a terminology. So this is called low density parity check. So what is low density parity check? So low density parity check code physically means that the Hamiltonian in your many body gap lattice model is local. So so each term in the Hamiltonian consists of like constant number of terms. So as your system size grows, the number of terms in your Hamiltonian is the same. And also each physical qubit only participate in constant number of Hamiltonian terms. So basically, this is what this low density parity check means. So the fact that the Hamiltonian is local is essential to realize the models in the lab. So this is a desirable condition in your common codes, and you want the Hamiltonian to be local. And however, it's actually well. So there's another desirable property. So in addition to for Hamiltonian being local, there's another desirable property. So if you increase the size of your quantum computers, you want the information stored in your quantum computers to also increase. So ideally, if you scale up the size, the information should increase linearly with the size. And also the number of errors you can correct in your in your quantum computers should also grow with the size. So otherwise, if you scale up the size of quantum computers, there can be many errors that you cannot correct. So that's not what you want. So what you want is that as you scale up your quantum computers, the number of errors you can correct will also scale up. So so these properties that Hamiltonian is local, and also you have these two properties combined together to be combined together to be called something to be called good LDPC code. So LDPC code means that Hamiltonian is local, and good means that you have these two properties. Now, however, this kind of good LDPC code is very difficult to obtain. So the only known examples are actually infinite dimensions. So you need to put the models on infinite dimensional spacetime. So that's not very practical, and it's very difficult to study this kind of code. And one strategy is one strategy invented by Freeman and Hastings is to map a good LTPC code to a Z2 gauge series, Z2 higher form gauge series on higher dimensional manifold. So instead of studying this complicated code on infinite dimensional space, you can focus on higher form Z2 gauge series living on 11-dimensional manifold. So the important thing to the important tool to understand this kind of practical LDPC code is to study higher form gauge series. So that's what I want to say. Okay, so let me skip this. Let me just briefly mention that, as I already alluded earlier, so in Zn higher form gauge theory, you can relate the poly-Z operator with the gauge field A, and relate the poly-X operator with the dual gauge field B. So this is the electric field, and the commutation relation between the poly-Z and poly-X will translate into the canonical commutation relation in the Zn gauge theory. And so in this way, you can write operators in Zn gauge theory using the gauge field. So for example, the Wilson line of A is just part of poly Z, but it can also have more complicated expression. So for example, this expression, roughly speaking, is think of it as the wedge product of the gauge field A with itself. And what it means is that this gives you a two-form. The value of this two-form on its square is given by this expression. So the product of A on this H01 and also together multiplied by the value of A on this consecutive H12. And similarly, you can have A on this 03 and multiply with the A on this H32. So together, it gives you an operator in this quantum mechanics system. And the nice thing is that it can convert this kind of technique can simplify commutation relation between the operators in this Zn gauge theory. So the commutation relation between this kind of operators with poly X. So recall that poly X is the electric field. So the commutation will just shift the gauge field A, and in this way you can unify many gauge identities. Just skip the detail. So let me back to the discussion of symmetry. So so as I already there are some I already gave you some examples of symmetries in the Zn gauge lattice model. But more generally, so suppose you want to apply a ordinary symmetry in your lattice model. So to apply this, we can apply the symmetry transformation on a finite region R, and then just grow the region R to enclose the entire space. So in this way, you can apply the symmetry in the system. Now, however, there's a problem. So if you apply the symmetry on an entire space, then you necessarily apply the symmetry on the entire logical qubit. So we call that logical qubits. So each logical qubit corresponds to some ground state wave function. So if you apply the symmetry on the all the physical qubit, then you necessarily apply the symmetry or logical gates on all the logical qubits. So in this way, you can apply the logical gates in parallel. So if you want to apply the logical gates in parallel, you want to apply symmetry not on the entire space, but just on some finite region, some submanifold. So this kind of symmetry that is applied on a submanifold is called higher-form symmetry. So if the submanifold has coordination Q in space, then it's called a Q-form symmetry. And similarly, we can apply the transformation on a finite region and then grow the region until it wrap this codimension Q submanifold. So this kind of higher form symmetry can be applied in parallel. So we can apply it on different submanifold. The submanifold can have different topology, and we can apply in parallel. So in this way, we can use higher form symmetry to apply many different logical gates and more efficiently. And so in this talk, I'm going to focus on invertible, like group-like unitary symmetries. So this kind of symmetries can always be implemented by a finite depth circuit. So it's a unitary circuit that has finite depth. So the way we implement the symmetry is the following. So if you apply the symmetry on a finite region, you create some defects. So there can be a pair of defect A and A bar. So A bar is the inverse of the defect A, such that together they can be annihilated by a finite depth circuit. So if you apply a transformation to create like many strips of A and A bar, you can connect those strips using finite depth circuit. So in this way, you can implement a symmetry on this entire green region using finite depth circuit. And as I mentioned earlier, symmetry, if the symmetry is implemented by finite depth circuit, then you will preserve locality. So if you have a arrow or excitations that happens here, if you apply a finite depth circuit, like the width of this layer is finite, the arrow will only spread in the finite region. So that means that this kind of symmetry or the corresponding logical gates is fault-tolerant, and this is what we want. Okay, so this is one motivation of focusing on this invertible unitary internal symmetry. And a large class of symmetry I'm going to talk about is the so-called gauge SPD symmetry. So we start with a gauge theory, like a ZN gauge theory. But more generally, it can be a general gauge group G. And I'm going to define a symmetry supported on some submanifold. So it can be some R-dimensional submanifold. And the definition is the following. So the operator is given by integrating over the submanifold with respect to some topological action of the gauge field. So recall that gauge field is related to like the Pauli operators in your lattice model. So the action of this operator on the state. So the state can be labeled by configuration of the gauge field. Is given by evaluating the Laplacian function of some topological action with respect to those gauge field configuration. So this is the definition
Can
of
I ask something?
gauges. Yeah, sure.
Is omega A necessarily a R form?
Oh yeah. So
Okay.
here you are integrating an R form over a R-dimensional manifold.
Okay, I see. Okay, thank you.
So an R can be arbitrary. Yeah. So if the space is if the space is 3 dimension, R can be like 1, 2, 3. Yeah. So in this way, by choosing different submanifold, you can define different operators. Yeah. So for example, if you have a torus, if the space is a torus, you can define a one-dimensional operator like wrapping on like this direction or this direction.
Okay, so it just needs
So
to be
in this way,
topological,
yeah.
right? It just needs to be topological.
Yeah.
Okay, I see.
Yeah. So this operator will generate a symmetry of your G gauge theory. So, and the symmetry will give you a logical gate. So in this way, by choosing different omega, choosing different MR, you can get different logical gates in your gauge theory. So let's give you a very versatile class of logical gates in your theory. Okay. So let me just
Before
briefly.
proceeding,
Mhm.
can I also ask a question?
Yeah,
So
sure.
when I first year SPT phases, I just come up with that the gauge group anomalies or maybe tooth anomalies. As far as I understand, in the previous slides, topological defect create a problem in our code, maybe an error. So is this the case for the gauge group anomalies in here, or maybe tooth anomalies?
So the tooth anomaly correspond to the boundary. So if the SPT has a boundary, you can think of the boundary carries a tooth anomaly. So tooth anomaly lives on the boundary of the SPT. Yeah. So here we have SPT on some manifold. So the system as a whole is still consistent, but the edge. So if the submanifold has a boundary, so here the submanifold can be actually closed or open. If a submanifold has a boundary, there must be some degree of freedom living on a boundary, and I'm going to discuss later. Yeah.
Okay, thank you.
Yeah. So actually, this is what I'm going. This is this next slide. So what's the input data? So one data is the cocycle omega. The other data is the submanifold M. So this, in order to define this logical gates or define this operator, I need omega and M. And moreover, if N has a boundary, suppose it's not closed, then I have to choose a boundary condition. I have to choose a boundary condition of the manifold. And by choosing different boundary condition, I can get different symmetry, or I can get different logical gate. So by varying these three ingredients, I can get I can classify the logical gates in my quantum codes, or the symmetry, or classify the symmetry in this gauge theory. Okay, so let me just proceed. So let me begin by considering case without boundary. So just considering varying the cocycle and the submanifold, and such that submanifold does not have boundary. I'm going to talk about boundary later. Okay, let me do it step by step. So well, let me just give you some examples. So let me still use the two gauge theory. So that's the simplest example. So it's a Z2 gauge theory. So what kind of operator I can write down? So if the manifold has one dimension, then I can write down it, then I can integrate the gauge field A over some one-dimensional locus, and that will give me the Wilson line. And these Wilson operators is the Pauli Z operators acting on the monomy of the Pauli Z gate. Let me mention here the bar means that it's a operators acting on the logical qubits. So the logical qubits are ground state wave function, and the logical operators acting on the logical qubits is denoted by a bar. So this is to be distinguished by the physical gates. So for example, the Pauli Z operator, this Pauli Z bar operator is the product of many physical Pauli Z operator along the yeah, so for example, this Pauli Z bar operator is the product of many physical Pauli Z operator for each edge along the cycle. So this is the physical Pauli Z operator acting on the physical qubits on each edge, and I'll give you a Pauli Z logic. Okay, so let me just give you some example. So this is one-dimensional submanifold. So what about other dimension? So let's say you have Z2 times Z2 gauge theory. And there's a gauge field A1 and A2. I can construct a two cocycle or two form given by which product, these two gauge field A1 and A2. So A1 cup A2 is a two form. You can think of as a wedge product. And we can integrate a two form over a two-dimensional submanifold. And previously I give you the definition of this integral. So if the two-dimensional sum manifold is the union of many small square, and on each small square, this integral is given by this wedge product. So this operator. So what's the meaning of this operator? So if you stare at this expression, you can see that if A1 has trivial holonomy, so if A1 has zero holonomy, then this operator will just be 1. And similarly, if A2 has zero holonomy, this operator will also be 1. So this operator is only non-trivial when both A1 and A2 have non-trivial holonomy. So this is called the, so in this case, it gives you -1. So this operator has a notation. It's called a control Z gate. So it's a Z gate controlled by one of the logical qubit. So if the logical qubit for A1 is 0, then you got trivial thing. But if the logical qubit for the A1 is non-trivial, then this just reduced to integral of A2. So this is the poly Z. So this is called a control Z gate. And so you can verify it's a control Z gate by studying the relation studying the computation relation between this operator and the poly X operator. So recall that the poly X operator is like the electric field, and a commutator with the electric field will shift the gauge field. Okay. So if the commutator with the poly X1, so this is the electric field that will shift the A1. So if you shift A1 by 1, you'll got A2, and A2 is the poly Z for the qubit 2. So we have this kind of commutation relation. Basically, this also tells you that you have this control Z gate. Now, importantly, you notice that So first of all, this operator is supported on a two-dimensional sum manifold. So this is integrating a two-form over a two-dimensional sum manifold. And this poly X, as I explained earlier, is also supporting on some one-dimensional sum manifold. So just flash back. So this poly X gate is given by product of X along for the edges that intersect a one cycle. So it's also one dimension. Okay. So this poly X is one-dimensional. This CZ is two-dimensional, and this poly Z is one dimension. So you see that the commutator of some one-dimensional operator with some two-dimensional operator give you some one-dimensional operator. Now you can generalize this relation. So instead of two Z2s, you can have three Z2s, and you can have similar operators. So this is now a three-form. You are integrating this three-form over some volume. And this will give you something called CCC. And you have this commutation relation, which is similar to a commutation relation that I told you earlier. So this new operator is supporting on volume. This X operator is supporting on line. And this CZ operator is supported on a surface. So we see that taking a commutator of a volume operator with a line operator gives you a surface operator. And those different operators supporting on manifold with different submanifold with different dimension correspond to different higher form symmetry. So this kind of mixing different higher form symmetries is a feature of higher group symmetry. So this is what this higher group means. So higher group just means that if you take the commutators of different higher form symmetries, you got different higher form symmetries. Like here you have a zero form symmetry, or here the symmetry is supporting on a volume. Here the symmetry is supporting on line, but here the symmetry is supporting on surface. So this kind of mixing the dimension is called higher group. Okay, so this is what it means. Okay, so let me just briefly. Let me also mention that so recall that the input data of this operator does not just have this cocycle, but it also has this submanifold. So by choosing different submanifold, can get different logical operator or get different symmetry. So for example, if you take this cocycle, so this is the transmester of the Z2 gauge field A. If the volume is a 3 torus, this operator is actually trivial. But if the volume is instead RP3, so it's the quotient 3 sphere by the interpolar map. If the volume is RP3, you actually got a poly Z gate. And similarly, by choosing like auto topology, you got different answer for this. So the operators depends on the topology in a very non-trivial way. Okay, so if you consider higher form gauge theory, then we need to consider cocycles or topological action for higher form gauge field. And we classify the topological actions for like one form gauge field and higher form gauge field, where the gauge group is part of Zn. Now, importantly, we realize that if you have even degree higher form gauge field, like 2 form, 4 form, 6 form, etc., you can write down a new cocycle. So we call it Pontryagin power. And we discovered this explicit cocycle expression for this cocycle. So this new cocycle will give you some new operators. So this operator depends on cocycle. So if you discover new cocycle, that'll give you new operators. And what's the importance of this operator? Well, it turns out that these operators give you some new gates. So this is called a control rotation gate. So poly Z is like 1 minus 1, like diagonal matrix with 1 minus 1. It can take square root of poly Z, and this is called a poly S, which is like diagonal matrix with 1i. And you can also take further fractional power, and it's called the RD gate, where R1 is Z, R2 is the square root of Z, and etc. Just keep taking the square root. So we find out this new cocycle can build this kind of new control rotation gate. So this rotation gate is the single qubit rotation, like poly Z and the square root of poly Z, etc. And what's the importance of this control rotation gate? It turns out that they are essential in quantum Fourier transform. So this is a circuit for a quantum Fourier transform. So if you perform quantum Fourier transform on like 1, 2, 3 many qubits, one important thing is highlighting is red. So actually it's a Hadamard gate, which is Clifford, the Clifford gate. These red things are 2 qubits control rotation gate. So this black dot is the control qubit. If the control qubit is 0, this gate does not do anything. If the control qubit is 1, then you perform a rotation. So you can see that there are many control rotation gates in the circuit of the quantum Fourier transform. And those control rotation gates can be implemented by this cocycle operators. So that's basically one application of this new symmetries. And also we can use this kind of method to get some new gates in detail. Okay, so now let me talk about boundaries. So previously, when I talk about this symmetry operators, I only mentioned 2 data. One is the cocycle, including this new cocycle I mentioned, and also the topology of the submanifold, where you integrate this cocycle over. But there's another piece of data, which is the boundary condition. So if the submanifold has a boundary, by choosing different boundary condition, you can get different operators, different symmetries, and different logical gates. So that's what I'm going to do next. Okay. So what are the boundary conditions we can choose? So we start with a gauge theory with gauge group G. And so let's say you have a submanifold with a cocycle omega. So what kind of boundary condition can happen? So the boundary condition is the following. So the boundary can break the gauge group down to a subgroup K. So you can think of some Higgs mechanism as some scatter on the boundary and break the gauge group G to K. But there's an important consistent condition. Because of the omega, because this cocycle omega, the boundary in general will have some gauge anomaly. And gauge anomaly is inconsistent. You don't want gauge anomaly. So you want to depend that the subgroup K on the boundary will be such that this omega, when you restrict omega on the boundary, on this subgroup K on the boundary, it has to be exact. So the restriction of omega on the boundary subgroup K has to be exact. So that's the condition on the subgroup K. So once you have this boundary condition such that omega becomes exact, you have a boundary condition of the operator, and then you define, and by choosing different boundary condition, you got different operators and different logical gate. Let's see. Well, let me just explain, give you some idea. So for example, if you have Z2 times Z2 gauge theory, so there is an operators a symmetry given by integrating A1 cup A2 or A1 wedge A2 over some two-dimensional submanifold. So this is your cocycle. And now I'm going to consider submanifold with a boundary. So this two-dimensional manifold now has a boundary. But what's the boundary condition we can choose? So for example, we can choose the boundary, or can choose the subgroup on the boundary to be the diagonal Z2 subgroup. So we break the G to a diagonal Z2 on the boundary. So this diagonal Z2 tells you that we set A1 equals to A2 on the boundary. So let's call it A. So small a equals to A1 and A2 on the boundary because they are the same. Now it turns out that because of some mathematical identity, this A1 cup A2 actually becomes an exact cocycle. So you find that this exact cocycle is actually of order 4. So you start with order 2 cocycle because its value is like +1 or -1. But on the boundary, you actually got a factor I here. So see that if you consider a boundary, like this particular boundary, you can actually got a operator, got a symmetry operator, or got a logical case that has order 4 instead of order 2. So by considering different boundary conditions, you actually open up like a floodgate of many logical gates that you can construct. So let me just give you one example. So if you consider like Z2 cube gauge theory, so Z2 cube gauge theory has a okay. Let me just go back to the example. Okay, right. So recall that Z2 cube gauge theory has this operator. So A1, A2, A3 are the gauge field for these three Z2s. So it's a three forms. You can integrate a three form over a volume. Okay. Now let's choose the volume. So let's allow the volume to have a boundary. So we can choose some boundary condition. And okay. So the volume is this tetrahedron. And we can choose the boundary condition by breaking the gauge group, breaking the Z2 cube gauge group to some subgroup. Okay, so by choosing these different boundary condition, you actually you can actually discover different extra operators on the boundary, like this extra A to the A on the boundary. But here you actually got more functional. So in this way, by choosing different boundary condition, you actually got arbitrary rotation gate. So Rn is like the somewhat like higher fraction power of the power 0. So by taking different boundary condition, you can get arbitrarily fine or arbitrarily fraction power of the poly z gate. So in this way, we can construct like new series of logical gates, symmetries on some manifold with boundary. So maybe let me just quickly wrap up. So I've discussed some applications of higher function symmetries and higher group symmetries in quantum computation via these gauge SPT operators. So let me just recap. So higher function symmetry is important to construct logical gates that can be applied in parallel. So instead of applying on the entire space, we can apply higher function symmetry on some submanifold. And this allows us to apply them in parallel. So we can some subset of qubits. And also the higher group symmetry describe the commutation relation between different higher function symmetry. And this commutation relations captures the commutation relations of gates. And also, if you gauge the higher function symmetry, I didn't mention that in detail, but as I briefly mentioned at the beginning, if you consider higher function gauge theory, you can actually construct efficient memory that can store quantum information more efficiently without the need of error correction. And and I have I have demonstrated that you can construct this kind of gauge SPD symmetry to realize many different logical gates. In particular, we can realize logical gates that are essential for quantum Fourier transform, which is widely applicable in so maybe let me stop here. Thank you.
Thank you, Po-Shen. We can take some questions if there are. Or maybe after stop recording, you can ask. If there are no more questions, we can stop here.
I have a
So again,
question.
thank you, Po-Shen, for the great talk. Okay, go, Po-Shen.
Do your boundary conditions correspond to Neumann and Dirichlet boundary conditions by any chance?
Yeah, so let me just recap what's the boundary condition. So we break the gauge group G to subgroup K, some subgroup K. Okay. So this is like partially Higgsing, right? So if K is trivial, so if you completely break the gauge group G, then this is the Dirichlet boundary condition. This Dirichlet boundary condition is completely break the gauge group G. And if the subgroup K is G, then this is the Neumann boundary condition. So here, if the cocycle is non-trivial, we cannot have Neumann boundary condition because otherwise you will have gauge anomaly. But in more general case, like the subgroup, when the subgroup K is not trivial or the entire group G is like sort of mixing Dirichlet and Neumann. And some of the gauge field is Dirichlet, some of the gauge field is Neumann. Yeah.
Yeah, okay, this was real descriptive. Thank you. So I have another question, if I may.
Oh yeah, sure.
Okay. So I think it was last week. There was a paper named SymTFT for continuous space-time symmetries. So in that paper, people realized that topological defects can actually realize the space-time symmetries. So how would that correspond to in the case of topological quantum computing?
I mean, it's an interesting question. I mean, I haven't really thought about that. So in topological quantum computing, we usually deal with internal symmetry. Yeah. So this is a bit different. Yeah. And because just think about how to implement space-time symmetry in the lab. Like you all have to sort of move the lattice or like perform time reversal. I'm not sure how to do it. So this is harder to implement on quantum computers compared to internal symmetry.
Yeah, I mean, I thought like your space was RP2, but maybe through some taking RP2 as a compact slice of the space-time, maybe R cross RP2, maybe it could be done, but I don't know. Yeah. Okay, thank you.
If there are no questions, we can stop recording, and we may take some questions after the recording. So thank you again, Po-Shen.
Yeah, thanks for having me here.
We can stop recording for now.